Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing. 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 All right, it's working. It's working. Then we just gotta wait for X. All right. Alrighty. How's it going, Ed? How's it going, Oma Viva, Niraj? You guys better be ready. This one's gnarly. All right. I think it's live on X. Let's see. Let's make sure it's working. Testing on X. Testing on X. Testing on X. Oh. Testing, testing. All right. I think it's live on it. All right. It works. Perfect. All right. Let's get this started. Getting just a little bit better at the didgeridoo every time. All right, guys, we got a stream for you guys today called Vidu4D. This one's pretty involved, pretty intense, lots of kind of intense computer vision math, but you know, if you're into that, then it should be fun. So this is going to be a stream centered around this paper here. This is a paper released the 27th of May. Kind of a grab bag of different Chinese institutions here at Tsinghua University, Shengshu. This paper is called Vidu4D, Single Generated Video to High-Fidelity 4D Reconstruction with Dynamic Gaussian Surfels. Okay, so dynamic Gaussian Surfels are the four-dimensional version of Gaussian Surfels, which is a stream that we did a couple streams ago. So we're finally now seeing the 4D version. Previously, we were looking at the 3D version. The single-generated video, the input for this model is going to be a generative video, which means a video that is generated by a video generative model, and video generative models generate from text. So really this is text to 4D Gaussian Surfels. All right, let's read the abstract here, and then we'll kind of dive into the introduction here. Video generative models are receiving particular attention given their ability to generate realistic and imaginative frames. These models are also observed to exhibit strong 3D consistency, significantly enhancing the potential to act as world simulators. Something you might have heard before. The whole video generative models are the new world simulators. In this paper, they present Vidu4D, a novel reconstruction model that excels in accurately reconstructing 4D, specifically sequential 3D, so 3D representations that have a time dimension, so a 3D representation over time, from a single generated video. At the core of Vidu4D is dynamic Gaussian Surfels, shortened as DGS. So you've heard of 3DGS. This is 4DGS, except rather than calling it 4DGS, they're going to call it DGS, just to be a little bit confusing there. But they're going to be warping these Gaussian Surfels into a four-dimensional version. they do a couple different tricks here. They have a novel initialization state. They do this warping. And ultimately, they end up with high-fidelity text to 4D generation. And they have this page. So let's check out their examples. So here we have examples. And we see that at the top here, this is a generated video, right? So this is generated with something like Sora, right? Or Stable Diffusion video. And the output of the model is the kind of mesh. It's not really a mesh, it's a distance function, but you can see it's a 3D representation of this video. And it's pretty good, right? Like, look at this cat. The normals on that are very clean. It's a very smooth surface. Kind of the best I've seen, to be honest, especially just from a video. So let's go back to the paper here. Video generative models exhibit strong 3D consistency and have a potential to simulate realistic environments. And we're going to look at Sora. So Sora is the state-of-the-art video model that really hasn't been released. The only thing we've seen from it are these demos. This was made by OpenAI, and it's a diffusion model that takes a text prompt. So this is like your prompt. You put in this prompt, and out comes this video, and it's like a minute long. And people got pretty excited when this came out because not only are these videos extremely high quality, like this, some of these are really amazing. Like, look at this guy running on this treadmill. But they're so good that people think that you might actually be able to use these to simulate realistic environments or use them as a world simulator. So anytime you see CGI or anything like that in the current world, that's all being done explicitly, right? You have this very complicated setup with tools, 3D engines, physics-based rendering. You have animation that's being done by hand. There's so many different little pieces that are all coming together. And we finally have technology that allows you to go directly from text to pixels without any of those intermediate representations being engineered or designed. So damn, I mean, these are so good. Every time I see these, like, look at that. Look at this growing. That is pure generative AI. There's no meshes or lighting or anything there. It's just straight text to pixels. And in this paper, they take the output of a generative video model and they're going to turn it into a more explicit kind of 3D representation so that you can render it in something like a VR headset or make it part of a robotics pipeline or something like that. Take a 2D video, turn it into a 3D representation. 4D reconstruction enables the creation of models that capture static scenes and dynamic sequences over time, crucial for applications such as VR. All right, here we have kind of more examples. The videos on their site are a little bit better. So obviously these guys don't have access to OpenAI Sora. Nobody really does. I think they gave special access to some of Sam Altman's friends, but nobody has access to this model yet. So they're going to be using a different one. They're going to be using Vidu. Vidu is basically Sora, but created by this Chinese company Shengshu, which literally has the Meta logo. That's like the Meta logo, but like the Chinese version of it. And it's not quite Sora, but it's good. You know, it's pretty good. I would say this is maybe a little bit better, if not on par, to Stable Video Diffusion. But not quite as good as Sora. Maybe not quite as good as Google's as well. I think Google has a video model that we reviewed as well that was pretty good. But, you know, it's all right. There's nothing in this technique that makes it specific to this Vidu model, right? So as soon as you have Sora or any other model that's released, you can apply this technique to it. I wonder what the quality of the objects from novel angles. They do have some examples of novel view. So here you have novel view synthesis, so you can see it's pretty good. All of these examples are all object-centric. So one thing I don't like about this paper is that in every single one of these, there seems to be a very simple single object like right in the middle of the thing, right? I'd love to see this with more complicated scenes, such as something like this, right? Like, can it get a mesh on all of these trees? Can it get a mesh for the ground? Like, the surfaces on the ground and the trees, like, those are more complicated. These, like, scenes are much more complicated for 4D reconstruction than something like this, where you have a single object that's kind of being rotated around. So, still early days, and this paper is definitely a little bit complicated, a little over-engineered, but to me, it really shows that there's a pipeline there. As soon as you have Sora, we're going to start to see much stronger 3D and 4D reconstruction papers, which we saw with stable video diffusion. As soon as you had two-dimensional text-to-image models, you saw this whole stream of 3D models or 3D generative models that came out where they were effectively using these two-dimensional text-to-image generators as data generators for their 3D models. So now we're seeing kind of the next level version of that, where you're using video generative models, which are generating 2D frames with a third dimension of time. And now this paper's turning that two-dimensional image with a third dimension of time into a three-dimensional representation with the fourth dimension of time. Okay, so you're like extending one dimension out of here. All right, non-rigidity and frame distortions are prevalent issues pretty much with all of these. Even with Sora, you have this issue. I think there's a couple examples where you can see it pretty well. Let me see if I can find one for you guys. Maybe this one? Yeah, this cat one. So you can see, like, if you kind of look, like, the details are a little weird. Like, you see how her arm kind of, like, turns into a fold, and this cat has, like, two paws that kind of turn into one another. So it still has all the weirdness of, like, generative AI, like these weird visual hallucinations and distortions and skipping and stuff like that. But I think those will go away with scale, so we don't need to worry too much. They're going to use Vidu4D. Novel reconstruction pipeline, 4D representations from a single generated video, and because that single generated video is coming from text, effectively this is a way to go from text to a 4D representation. They're going to have to initialize these non-rigid warping fields. We're going to get into that. It's probably the more complicated part here. Warped state normal consistency regularization to align the surfels with actual surfaces with learnable continuous fields. By the end of this stream, you're going to know what every part of that is. And then they have some refinement. Okay. We're actually going to go through the related work section this time because I think that having a little bit of historical kind of background on this is going to make this make a little bit more sense. Okay, so initially triangle meshes were favored for their compactness and compatibility with rendering pipelines. So I have here triangle meshes. Triangle meshes are the way that we do 3D, the way that we've been doing 3D forever now, right? So basically you have this very explicit way of storing 3D information, which consists of two pieces. You have a mesh, which is composed of these triangles and vertices, and then you have a texture, and the texture is mapped to each of these kind of planes that are defined by these triangles. And this is how you get textured meshes, which are pretty much how we do everything now. Every single movie is using this. Every single video game is using this. But then we had the introduction of neural radiance fields, which are an implicit volumetric neural representation. So then there was the NeRF craze. Here's what a NeRF is. A NeRF is a little multi-layer perceptron, or a little neural network, a little deep neural network, because it has multiple layers. And this little neural network allows you to implicitly store an object inside some volume of space. And the reason we say implicit is because you don't actually know what the object is until you render it, right? It's like there's just a bunch of numbers inside the weights of this little neural net. And those little numbers, if you plug in a specific XYZ coordinate and a specific camera view angle, this theta and phi here, it'll give you effectively a color and a density. Density is kind of like how see-through it is, right? And if you do that, you project a bunch of rays through each of the pixels in a two-dimensional projection into your volume of space, and then you perform a bunch of inferences of this little multi-layer perceptron. You can do some volume rendering, which is effectively kind of just a fancy way of saying you're adding together all the colors along this ray, and you can get a two-dimensional picture of this object, which is stored implicitly in the weights of this little neural net. And these were really popular. NeRFs, kind of when they came out, everybody was like pretty obsessed with them. We thought these would be the end, or these would be the new way that we do everything, right? There was kind of the deep learning craze. They hit right when, right before kind of GPT and that deep learning craze. But we had one more switch, and the next switch was 3D Gaussian splatting. 3D Gaussian splatting is more like the vertices here because it's much more explicit. So here I have a Gaussian splat of this little Unitree robot, and if we zoom in, you can actually see what Gaussian splatting is, right? Gaussian splatting is these little splats, little three-dimensional Gaussian splats, which is why they're sometimes called 3DGS instead of Gaussian splatting. And because they're more explicit, and because of certain properties with GPUs, you can actually render them much quicker than NeRFs. So NeRFs, the Achilles heel of the NeRF is that you have to perform a bunch of inferences on this little multi-layer perceptron for every single point along a ray, and then every single ray for every single pixel. So that's a hell of a lot of inferences on this little multi-layer perceptron, which means that NeRFs in practice are a little bit slow. And they're also implicit, which means that it's very difficult to do kind of like high-level stuff, right? So like you can't remove the floor from this object and put this object on a different floor, or like doing any kind of thing where you're moving parts of it, taking parts out, moving parts in, right? Changing certain properties of it. It's a lot easier to do that if you have a more explicit representation. And that's why these Gaussian splats, I think, become more popular, right? They're faster, they're more explicit, which means you can kind of compose them, you can edit them. It's easier to add lighting effects or view-dependent lighting effects. So splats were a thing for a while. And now we have the evolution of splats, which are called Surfels. And Surfels are pretty new. I think it's just the last couple months, but they've been around for a long time. So Surfels are actually really old. We have here the original Surfel paper. I think it's this one here. So the original Surfel paper is actually the early 2000s, like 2001, something like that. And Surfels are very similar to splats, except now rather than having a three-dimensional splat, you're basically using this little you can think of it like a little disc, like a little coin, right? And that little coin is kind of aligned along your surface. And the advantage of this is that you can use, or Surfels have a very specific normal direction, right? There's a very specific alignment of that little coin, as opposed to something like a Gaussian splat, which is 3D, right? So it doesn't really have that same, you see how here the alignment of these Gaussian splats, like they're not all aligned with the surface. They're all just kind of like scattered there, right? Versus something like a Surfel has a very specific alignment, which means that you can use the fact that everything is on a surface and kind of get better regularization using that normal and the surface. And if you actually want to know where the name Surfel comes from, here's a 2021 paper. Surfel actually comes from surface element. So that's what it means. It's a surface element. It's like a little disk that's sitting on your surface, has a very specific normal vector. Here's the normal vector. And then some point P. Okay. So we went from triangle meshes, very explicit, very slow. Not great for a variety of reasons, but great because we use them in practice all the time. Then we went to neural radiance fields, NeRFs, which were pretty cool, but they're very implicit, so they're kind of hard to use, and they're slow to actually render. Then we went to 3D Gaussian splats, which was a little bit in between, right? Explicit, but you're still using kind of, you're learning them, so you don't have to hand engineer in like these triangle meshes, right? Like the problem with these meshes is these are made by hand by a modeler and then animated by hand, all this crap. So 3D Gaussian splatting has some advantage there. And then now we finally come to the best version of all of this, which is Gaussian Surfels. And that's the story. That's the story of 3D representations. And in this paper, they're going to take Gaussian Surfels and move them from just a static scene. So this is a static scene, right? There's nothing moving here. It's just a static 3D representation into a 4-dimensional Gaussian surfel. So you can see this is now 4-dimensional. You've added that extra dimension of time. Okay. All right, so that's a little bit of history. Traditional methods have explored dynamic reconstruction using synchronized multi-view videos. So traditionally, whenever you want to do 4-dimensional reconstruction, aka generate something that's 3D but in time, you usually need multiple views, right? So you have synchronized multi-views. You have the same scene being filmed from multiple camera angles, and then you can kind of just use basic key point matching and triangles, camera geometry to get 3D information from that. But in this paper, they're only going to have a single view, right? Monocular is just the single view is the generated video. Okay. Our work introduces dynamic Gaussian surfels, leveraging video generative models to achieve generation capabilities, preserving high-quality appearance and geometrical integrity. All right, and now we're going to go into the method section. So that was just the introduction, a little bit of background on 3D representations, 4D representations, reconstruction. But now we're going to get right into the meat of it. This some pretty gnarly math, so we're just going to get into this. A single sequence of RGB video with T frames. So this is what's coming out of your Sora or your Vidu, right? It's just a sequence of T RGB video frames. And we want to turn it into a sequence of 3D representations. So we still have this discretization in time. So time is being discretized into these frames, much like space is being discretized into pixels, or 3D space is being discretized into these surfels. We're discretizing time into T frames. The Tth frame at time T is parameterized by theta T. So there's some parameters that you're going to be learning over time. You have some differentiable rendering mapping G and a frame pixel X bar T in R2. So R2 here means this pixel's just XY. It's in image space, right? So it's in this space right here. This is X or UV space, XY space, right? The just 2D space. And here we have the general formula for how this is working, right? So C hat X bar T here is going to be the rendered color or observed color. So it's like, what is the real color, the color that you see inside your generated video. And then this here, C X bar T, this is the color that you get from your DGS or dynamic Gaussian surfel or 4-dimensional Gaussian surfel. So your loss function L here is basically going to be some reconstruction loss. It's going to be a little bit more complicated than that, but you're basically saying, okay, the color of what comes out of my Sora needs to be the same as the color of what comes out of my representation. So slowly over time, I'm going to be pushing gradients into this theta T, the parameters that are used alongside the points by my rendering function G, which is differentiable so that you can push gradients through it, because this loss function eventually pushes gradients through this G into this theta, and that's what this is, right? You're just slowly pushing gradients into that theta, slowly changing those thetas until you get this C and this C to be very, very similar. And you're summing this over all points, X bar T. You see here 3-dimensional points, R3, although I think X bar is R2. So over all pixels, X bar, for all frames, T1 all the way to capital T. So if there's 30 frames in your video, you're doing this over 30 frames. If there's whatever, 28 or 100 pixels by 100 pixels, obviously going to be more than that. Then you're summing over all pixels, over all frames, and you're finding the theta, the parameters of your surfels that minimize all of that, or minimize this reconstruction here. Okay. What are dynamic Gaussian surfels? Using differentiable 2D Gaussian primitives as proposed by recent Gaussian surfel advances. Okay, so there's the reference to the Gaussian surfels. There's going to be K total Gaussian surfels. Each Gaussian surfel is going to have a bunch of parameters, and these are the parameters that are in this theta T. So this theta T, which are the parameters that you're going to be optimizing over the course of this, or learning, consist of a central point, pk. The central point is this p right here. It's just this, where is this Gaussian Surfel in 3D space, so that's why it's R3. You have two principal tangent vectors, tu star and tv star. Those are basically the two, let me see if I can get a nice picture of this. I think the picture in the paper probably is nice. But you see here how every single little Gaussian Surfel has a little vector TV here and TU, so it's basically the two orthogonal axes on the coin, so kind of the principal coin axes. So the ones that are orthogonal to the normal vector. You have some scaling factor, SU and SV, which allows you to make kind of elongated coins and then also kind of like round coins, right? Allows you to kind of like take that circle and make it an ellipsoid. Here we use the notation star to represent the static. So whenever you see this star, it basically means the static state, aka something like this, right? Where it's static. And then the non-static one is not going to have that star. Okay, so the 3D one is star, non-3D one, non-star. For any point u, uv, so now this is a 2D point, which means that in the uv coordinate system, that's the coordinate of your camera frame, right? So when you're actually taking a picture of this, there's pixel coordinates, which are separate from the actual 3D coordinates of the world. Denoted P star KU in 3x1. Okay. You have rotation matrices here. So your point is going to have some scale times each dimension. So you see how in U and V, which are basically the dimensions here. So this is the U dimension, this is the V dimension. Right, in this two-dimensional space of this little Surfel, and your scale is kind of warping either the U or the V. So here's your scale warping the U, here's your scale warping the V, and then you can turn that into a rotation matrix and a scale matrix. So they're basically just taking these the principal tangent vectors along with the scaling factors and turning that into a little SO3, which is just a Lie group for rotations. Diagonal matrix S denotes the scaling matrix. All right. They reconstruct from a single generated video, which may exhibit significant non-rigidity, distortion, or illumination changes, right? And those will go away over time. Like slowly over time, we're going to get rid of the hallucinations, the visual hallucinations that you get from generative video models. Much like initially when we had image generation models, there was all kinds of weirdness, like multiple fingers, was the kind of example that everybody knows where you generate hands with 5 fingers or 6 fingers, right? There's extra teeth, like weird things going on. But modern generative image models don't have the same issues anymore, right? Most, like, I don't know, DALL-E 3, Stable Diffusion 3, if it ever comes out, those are going to generate 5-fingered hands. They kind of solve that problem with scale. So I think a lot of these problems are going to get solved with scale as well on the video generative side. Okay. Now we're going to get into the kind of more complicated part of this, which is going to be this warping. So we're going to have to learn this non-rigid warping function conditioned on time t and coordinate u. Okay, so the warping function is going to be consuming the time t, which is effectively just the frame, but you're not feeding the actual frame number, right? You have some position embedding for that, or maybe just some normalized time, and the coordinate u within that. So where inside that little splat are you, right? So you see this right here. We can zoom in a little bit. Zoom in into this image. See the u kind of defines a point on this Surfel. And the reason we're defining this point on the Surfel is because whenever we actually do volume rendering, we're still doing this with rays. So U here is an intersection with a Gaussian Surfel and a ray that emanates from the frame pixel. So in your head, you should be thinking very much like this, right? Where you have a ray. The ray is this like vector here with a direction, right? So the ray is coming from the camera. It's going through the camera plane, which is what you actually want, right? You actually want the value for this pixel. And it goes through some volume in space. And for a nerf, you're just querying it with a specific position in space, right? But in this case, you're going to be giving it u right, which is the intersection of the surfel with the ray. So you can think of that ray going through this scene, and it's going to be intersecting these little surfels at some points, and that point that it intersects that surfel with can be defined, right? It has some kind of coordinate with respect to the center of this little surfel, right? So within the coordinate frame of this little surfel, the ray intersects that surfel at some point u, and that point u, you're feeding that along with the time t into this warping field, which is going to warp this little surfel for you so that you get this nice little smooth surface. Okay. Warping techniques on each Gaussian surfel. Transform the static surfel. So you see here the static, because it has that star, it'll transform it into a warped surfel that doesn't have that star. So now you have p. You've replaced that star with time t at a time t which is centered at pkt. So p star would be the static one, pkt is the time one. And anytime you're doing this kind of static, non-static, that is a kind of bias, right? We've seen this kind of bias before when people first started taking generative image models and turning them into generative video models. You saw this pattern a lot where basically there was a static representation of the image and then some regularization that was taking that static image and then making sure that every single frame in the video kind of looked like that single keyframe, right? So you have like this idea of a static scene, and then all of the other frames should somehow have some regularization that forces them to be like that single keyframe. And that really only works for scenes where there's not a lot of movement, right? So these type of regularizations to like a keyframe, they're not going to work well if you have something that changes a lot, right? So like in the scene, all of these scenes, like these scenes are pretty fine, but like maybe something like this, right? This scene, like the scene changes a lot, right? You have like new people appearing, you're like changing, things go in and out of view. It's going to be a lot harder to have something like, you're not going to be able to do this same kind of approach where you have like a static or keyframe that you're kind of like using to regularize all other frames in your video. So still early days for this, but I don't know. I thought that this was pretty cool. All right. Non-rigid warping for Gaussian surfels. Okay, so now we're going to define a time-varying non-rigid warping function by leveraging bones. Okay. The Beath bone is represented by 3D Gaussian ellipsoids. Okay, so they're going to have these bones that are effectively going to be like little Gaussians, right? They're going to have some center, some rotation matrix. What is a bone? All right, so a bone is this. So in the classic texture mesh representation format like this, right, in your video games that you play, when you hear the word bone, this is what they're talking about. So a bone is this little link right here, right? And whenever your video game character like performs some animation, that's an animation that was basically designed by hand, frame by frame. So you had a guy, they're known as animators, who basically puppeteer these virtual 3D objects via the use of these bones, right? So these bones allow you to kind of say, okay, I want the arm to move down, and there's a relationship between all the little vertices on this arm and that bone that allow you to kind of like deform the mesh in a way that produces this animation, right? This is for textures and meshes, but bones as a kind of like an animation primitive have seen continued use. And here you have a 2022 paper by Meta AI, Carnegie Mellon, Meta Reality Labs, where they also have these bones, right? And they're using these bones to animate this, I don't know if it's a mesh implicit canonical 3D shape. It might be a surface. There's a lot of different ways to represent a surface, but they're going to be basically using these bones, right? So they're going to have bones that are going to allow you to kind of determine the motion of this object. And each of those bones is going to be like a little Gaussian. So the same way that you have a bunch of little Gaussians that are defining these surfels, that are defining the surface of your object, you're going to have a bunch of little Gaussians or 3D points that you're learning over time that are defining the kind of like the movable parts, kind of like the larger chunks of the actual object that you want to be moving. So they're baking in the animation into this optimization process. Each of these 3D Gaussian ellipsoids or bones is going to have some center CB, some rotation matrix VB, and you notice how all of these are defined in the static frame, so the key frame that you're regularizing everything with respect to, and a diagonal scaling matrix lambda B star. So a little aside here, this is one of the cooler Greek letters. So this is the capital letter lambda, and the capital letter lambda is actually what the Spartans put on their shields, because Sparta was actually, in Greek, I think it's called Laconia, and the L in Laconia is lambda, so the capital letter lambda looks like an upside down V. So I don't know, pretty cool Greek letter to use, the Spartan letter. All right, do you think the Spartans would guess that their logo is being used to define the scaling matrix for a 3D Gaussian bone inside a 4D Gaussian Surfel paper in the year 2024? I don't know if they would have predicted that. All right, so you have some JBT, SE3, another Lie group representing the rigid transformation. Then you have some skinning weight vectors, WT. Okay, so what are skinning weights? This is skinning. So here you have some bones, bone 1 and bone 2, and you have these vertices. So we're inside the textured mesh 3D representation. And you want to know, how should I move the little vertices of this mesh with respect to each bone, right? So whenever I move this elbow bone, which of these vertices are moving and which are not moving? And that problem is this problem of skinning, right? Like, so which of these meshes move with respect to which bones? And that's usually done with skinning weights. So you can see here, this is someone in either Blender or some kind of program like that, and they're selecting different bones inside this armature, and they're saying select influence, and what they're showing you here is the skinning weight. So you can see that these vertices up here have a high weight with respect to this bone, but these vertices over here in the edges have a slightly low weight. So each vertex is being influenced by multiple bones depending on the weight of that skinning weight, right? And this is kind of an art more than a science, to be honest, because there's a lot of potential issues if you pick the wrong kind of skinning weight for the bones, right? So like the kind of classic stuff here is such as this one here. This is a paper that we'll look at in a second. But you can see here, sometimes in old video games, you'll see this, like you see how this shoulder, when you do this double rotation of just going like this and then this, the vertices of that kind of warp in a weird way, right? So like you're moving these bones that are underneath this skinned mesh, and because the vertices are mapped to specific bones with specific weights, sometimes you end up with these weird situations where you have multiple motions and you end up with what's called candy cane. I think there's a specific name for this. Candy wrapper artifacts, right? Where you kind of rotate and all the vertices kind of like collapse into the bone. It also happens a lot with elbows, right? So like sometimes you get these weird elbows. That's because you're really just defining the animation in terms of these bones, and then you're relying on your skinning to appropriately transform the vertices of your mesh such that they follow the bones, but you can't just rely on these skinning weights, especially when they're designed by a human, right? Some human is going here and kind of like manually painting the weights, the skinning weights. So in this case, they're going to be learning these, right? These are going to be properties of these bones, and they're going to slowly push gradients into these over time. How's it going? Something, an 87. Question from something something. I would assume I'd be easier, at least for now, to use real video to train to make the 4D representations. Yeah, you're correct, something something. You could definitely take this approach right here, and rather than using a generated video coming from a generative model, you could just use a real video and then probably get a nice little 3D shape from it, right? You could get a nice little 3D representation or 4D representation, which is a sequential 3D, aka 4D. But the reason they want to use video generative models is because what they really want to do, we eventually want to get to a point where we're doing this, text to 4D, right? Right now, if you want 4D, you have to basically make it explicitly. You have to have someone that actually makes the 3D model, and then you have to have someone that skins the 3D model, that puts this armature, these bones in here, and then you have to have someone that like deals with all this issue here with the skinning weights. Like our entire like 4D pipeline is composed of all these little steps that involve not just kind of engineering, but also like artistic skill, right? Like all of these things, whether it's animation or skinning, like modeling, like there's a human expert in that loop who's been doing this for like 30 years and is like basically an artist, right? Like almost like someone who like chisels marble or like shapes with clay. There's, I think 87GN is talking about, there are kind of like programs and like heuristic little things that people do, like tools inside these programs that allow you to kind of like more effectively create these skinning weights, but it's still largely being done by hand. So if we can figure out a pipeline that allows us to go from video generative models straight to these 4-dimensional representations like this, we just completely refactored the code stack, right? Like all of the 3D tools that we use basically don't matter anymore because we now have a way to do it end to end entirely inside an optimization process with deep neural networks, which I think is where this is all going, right? I think, and it's kind of scary to think about too, because there's a lot of money and people who are invested in the current format, right? There's a lot of people, like think about Unreal Engine, Unity, Blender, Maya, like all of these programs are all based around this idea that you have these textured meshes, you have these bones, you're animating these bones, you have humans that are animating the bones, you have skinnings. Like as soon as we get to the point where video generative models are good enough that we're using them inside these types of Vidu4D, and you're just getting the 4D from free, we've now like cut all of that stuff that I just described at the bottom, and you don't need to do any of that anymore. Right? And that's why people are excited about video generative models acting as world simulators, right? Where, hey, if you wanted to make a simulation for a robot, right now you have to do it all by hand, right? You have to put in all these different meshes, you have to have all this behavior, you have to have physics. Once you get this, you don't need any of that anymore, right? You're just end to end, all of it is inside some neural net. There will still be a craft involved in making this stuff. It just gets more meta. Kind of like, I think that it'll be, if we take generative image models as kind of an example, right? There's still a craft in using generative image models correctly, right? It's become kind of prompt engineering, right? Where like if you have the eye and the taste to be able to kind of describe what you want in more words and in more detail, you can generate better images than someone who doesn't know how to do that. And the same thing is going to happen for 3D, right? Where someone who has kind of an idea of what they want and they're better able to describe it, they're going to be able to generate kind of 4D representations better than someone who doesn't. But it's going to be so much easier to do that I think it's going to be a democratizing moment, right? Like anybody now can create super awesome fantasy art because generative image models have made that extremely accessible, right? If you can speak English and like vaguely describe what you want, you can generate very high quality stuff. So once we have this pipeline here where we're using video generative models to create a video and then using something like Vidu4D to take that and turn it into this four-dimensional, more explicit representation, then now you can make entire video games with just text. You can literally sit there and talk to the computer and create a video game, rather than right now it's extremely complicated because there's all these different parts. Yeah, Comfy UI is already so complex. It's much more than just prompting. Yeah, there's definitely complexity, but I feel like the complexity over time goes away, right? Especially if you start thinking about kind of more agentic workflows. So rather than you using Comfy UI, right, think about the next generation of kind of agents, right, where there's like a little LLM agent that's like sitting there that's using Comfy UI for you. So rather than you having to know what each of those little knobs in the UI is, you can say, okay, well, actually, I want this thing to be like that. And it's like, okay, here, let me change this little hyperparameter here. So I think over time, these things get simpler and simpler and simpler, especially once you start having agents that are kind of using these tools for you and like kind of guiding you through this process. Okay. So we were talking about the capital letter lambda and the Spartans. We were talking about skinning weights. We have normalized Mahalanobis distance. It's a pretty fancy name, but Mahalanobis distance is actually a relatively simple concept. Here you have Euclidean distance. Euclidean distance kind of treats every single dimension equally. So you see here how x and y defines kind of a circle around here. But Mahalanobis distance pays attention to the principal component. So there's some dimensions here to this data. The data is this blue point, and those dimensions correspond to some principal components, right? You put this into PCA, you would get one vector that goes this way, one vector that goes that way. Mahalanobis distance accounts for that, so it's a little bit smarter than Euclidean distance. So that's why they're using it here for these skinning weights and these bones. All right. You have a precision matrix composed of the bone orientation matrix. So these bones, right, are just little ellipsoids, so they have some orientation, some scale, some center. And C, which is the center of the bone, V, which is the rotation of the bone, and lambda, which is the scaling of the bone, are learnable parameters. So these little bones are, you can basically think of them like little Gaussians, right? Like rather than having I don't know what I was about to say there, but these bones are just like any other part of this where you're kind of learning them over time. Just like these surfels are being learned over time and you're kind of pushing gradients to slowly over time get better and better estimates of the central point and the scaling factors, the bones are the same way too. But there is a hard-coded number of bones. That is something that is a little bit annoying here, is that they basically hard-code 25 bones. So if you have something more complicated, you know, it would be great if you could add and remove bones. And we saw that in most Gaussian splatting papers, you have these kind of densification and sparsification strategies, which are adding and removing Gaussians, right? So like you can add or remove Gaussians from your scene, so you can take an area that maybe doesn't have enough Gaussians and add more Gaussians. So a next level version of this would be doing the same thing with the bones. You would be adding and removing bones over the course of the optimization process, because some scenes are going to require more bones than others, right? Like maybe for this monster, you can envision wanting to have bones for every single one of these spikes. For the fish, right, you definitely want bones in the flippers and stuff like that. So like there's going to be a different number of optimal bones for every single scene. So right now it's just hard-coded to a specific number of bones. JTB is achieved by a multi-layer perceptron. The MLP strikes back. So in a way, this is actually kind of like a little nerf, you know, because the little multi-layer perceptron is kind of how you're determining this warping. So no matter what, we can't seem to run away from these implicit representations of, in this case, the warping, you know. Okay, they're going to be applying dual quaternion blend skinning. Okay, we got another tangent here. What is dual quaternion blend skinning? Dual quaternion blend skinning comes from this paper here, This is also pretty early. This is a 2008 paper, I believe. Skinning with dual quaternions. Dual quaternions are a novel GPU-friendly skinning algorithm based on dual quaternions. Okay. So a dual quaternion, here is a standard quaternion. Quaternion is 4 numbers that represent a rotation. You have I, J, K, and then this W here. A dual quaternion can also be considered as an 8-tuple of real numbers. So it's 2 quaternions. So 2 quaternions are 4 numbers each. So 2 of them means there's 8 numbers total. All right, that seems fine. But later on, I was a little bit confused because they were like, okay, our little MLP directly outputs a 6-dimensional dual quaternion. I was like, wait a second. That doesn't make any fucking sense. You just said dual quaternions are 8-dimensional. So how are you getting a dual quaternion from 6 numbers? And I found the answer to that. You can also represent a dual quaternion in kind of like an axis angle or a screw motion. So rather than saying here's 4 numbers that represent a quaternion, you can say here are dual unit vectors and dual angles. And that's how they're getting 6 numbers to represent a dual quaternion. This paper is quite intense. Okay, so we have WT. WBT is the bth element of WT. So WT is your skinning weights, right, which is this. So your skinning weights, that's something that you're optimizing. JTB is your rotation or your warping, which is achieved by a rotation matrix and translation. Or for the bones, sorry. Q and R denote the quaternion process and the inverse quaternion process. So you're basically turning this into a quaternion and then turning it back into this J. So you're going J to quaternion, then back to quaternion. And when you do this, you guarantee SE3. So they have a little definition here in the quaternion paper. When you take the linear combination followed by a normalization, this is called dual quaternion linear blending, and DLB always returns a rigid transformation because DLB computes a unit dual quaternion which can be subsequently converted into a rigid transformation matrix. So subsequently converted to a rigid transformation matrix, that's what's going on here, right? This quaternion that's coming out of here is turning into, using this R, you're turning it back into this rigid transformation SE3, which is the Lie group. Okay. The intersection of the Gaussian Surfel and the ray. So this is what we were looking at before. All right. Maybe use 3D software to get multi-view to get depth and texture, but only allowing the model to see one angle. Maybe combine that with a frame masking. We might be closer. Something. Yeah, I mean, you guys, like, most of what you guys are describing here is like you're always going to be able to push performance by adding more engineering, right? And this paper is very engineering heavy. There's a lot of different pieces here that you're moving, right? You have these bones, you have each of these things, you have this 2-step process here. Like, I tend to be of the opinion that you make progress through simplification and scale. So even though this process looks kind of complicated right now, a lot of this has to do with the fact that you have to kind of make up for the generated video not being pretty good, right? Because the generated video has these non-rigidity, distortion, illumination changes, they make this problem more difficult, and so you have to have this kind of warped state, normal regularization. You have to like have these extra little pieces here. But once these generative video models get an order of magnitude better, which I think is inevitable once you train them on an order of magnitude more data and they're an order of magnitude larger, then this entire pipeline becomes simpler. And at some point, we're going to effectively get to a text to 4D where you can just basically talk, that'll get turned into text, and that text gets turned into a 4-dimensional kind of like surface more explicit representation that you can render on your VR headset. Okay. All right. what is the warp state normal regularization? They need to add normal consistency regularization that encourages all Gaussian surfels to be locally aligned with the actual surface. So the normal is this thing here. It's this little vector that is basically sticking out of the little surfel, right? It defines kind of the orientation. And the normal is actually one of the biggest advantages of surfels over NURFs, because now that you have this little normal, you can basically align the surfaces with this normal vector. So you can use the surface of an object, or effectively all the other normal vectors of these little Gaussian surfels, to act as a regularization on each of the little surfels. Okay. So you have your warping function, which we saw earlier, which is based on this dual quaternion blend scanning. JB is a continuous field that takes both the point and the time as conditions. So JB is a continuous field. What that means is that it's a little multilayer perceptron, as they said here. And the little multilayer perceptron is just a function, and that function can be evaluated at any point, right? So any little MLP like that, it's a continuous function in that you can plug in anything and it'll give you anything back, right? It's like it's a continuous input and output, aka some field. And in this case, rather than in the case of a NURF where it's taking the XYZ position and the camera view angle, in this case what you're giving it is the point PK star U, so the static kind of keyframe surfel, and then the time or the frame. So it's not really continuous, because this time t is discretized, right? Because you're discretizing time into frame, and then these surfels are also in a way discretized, because ultimately everything in a computer is discretized because you have some limited precision. You're storing things as bits. So even a 64-bit float is really not continuous because there's some discretization to that. Okay. Using a NURF-style MLP, which directly outputs a 6-dimensional dual quaternion. So here's your little MLP. It's being conditioned on U, which is the point of intersection of your surfel and your ray. So your ray is going through your volume of space. It's intersecting this little surfel. It's giving you some coordinate frame U within the coordinate frame of that little surfel. T is the time coordinate, basically. You're feeding that along with this learnable latent code. Learnable latent code is just a fancy way of saying some vector of numbers that doesn't really mean anything to us, but it's learnable, and it's going to allow this little MLP to kind of have an understanding of what's happening for this bone. So like, it's kind of like a way to say, okay, this bone is representing like the ears, or this bone is representing the tail, right? It's giving this neural net a way to kind of like put higher level information into this little MLP. Okay, what else we got? We got WK, which is the blending weight. NK is the normal of the surfel. Capital NT is the surface normal. And the depth point P at warped state time T. By learning a continuous warping field and aligning the surfel normal with the estimated surfel normal in the warp state, we ensure that all Gaussian surfels locally approximate the actual object surface without being noticeably impaired by the non-rigid warping. Okay. Pretty gnarly. Reduce the texture flickering. We learn refinement steps for adjusting the rotation matrices and scaling matrices. We suppose the refinement terms are delta RK star and delta SK star. So you see here how there's basically two different paths for gradients here, right? So you have gradients coming in and changing the center and scale of each of these little surfaces via this warped state normal regularization. So you have a regularization loss that's making sure that the surface of this object is smooth and doesn't exhibit weirdness, right? Making sure that the little normal vector for each of these little surfels is good. And then you also have your standard kind of loss here just coming from just trying to make this look like the video, right? Just trying to make sure that color matches. It actually kind of looks like what the fuck it's supposed to look like. So you have two different joint training. So gradients coming from here, gradients coming from here, and both of those are pushing into the center and scale of these little Surfels. And you can see here, here's the delta R, the refinement, delta R, delta S. Your change in the rotation and change in the scaling. Doing this in 2 branches, one with refinement, one without. Both branches are jointly trained and shared warping functions at the center of the Gaussian primitives. Okay, now you finally get to rasterization. Given a frame pixel X bar and a camera ray that emanates from X bar, so now you're thinking like a nerf, right? You have some ray pixel X bar, or you have your pixel X bar here in the camera space, 2-dimensional camera space, and you have some ray that goes through that. Volume rendering integrates alpha-weighted appearance along the ray, so very similar to a nerf here, right? In this case, the density is kind of like the alpha. You're looking at all the Surfels that it intersects, and you're basically saying, okay, the final color of this pixel is going to be some alpha-blended combination of all the little Surfels it intersects. So it's very similar to a nerf in that way. Alpha K and CK denote the color and the opacity. And of course, the color can't just be the color. It's going to be a spherical harmonic view-dependent color, which pretty much all these papers have. Okay, what do we got here? Static state, warped state, forward warping, initialization. I still just don't like this static state, like the fact that all this regularization is being done to just like make sure that your static state is always the same, like especially because the static state is very explicit, right? If your kind of keyframe was encoded into some embedding space and everything was being regularized towards that kind of like encoded representation of the kind of scene, I would be more comfortable with this. But the fact that everything is being you have these regularizations coming from this static state, which is being very explicitly stored in this representation that is a Gaussian Surfel. That's why I feel like this won't work well outside of very simple kind of like object-centric things like this. The camera trajectory of the generated videos is unknown. SFM methods like Colmap struggle to converge. This isn't 100% true because I've seen people feed Sora videos into traditional reconstruction kind of SFM pipelines. SFM is structure from motion. This is like taking a monocular video, maybe someone that's like flying a drone around a building, and you can effectively use triangles. And by that, I mean that you're looking at you're calculating all these camera triangles and then basically saying, okay, if this distance from here is this and this distance from here is this, then that means that these 2 points are the same. And if those 2 points are the same, then therefore we can kind of get an idea of like how much the camera has moved, right? And where this point is in 3D space, right? So multiple views or one camera moving allows you to do, get structure, aka the relationship between these different key points from motion. And that's what an SFM is doing. This is like kind of classic computer vision. So even though here they're saying that, hey, you can't really feed a Sora video into these classic SFM pipelines because they kind of move and warp, I have seen that. I have seen people feed them, and they do work quite well. So maybe it's just because their thing kind of sucks, but I feel like it eventually go away. 2 key stages, field initialization stage and the DGS stage. We first train a neural SDF. This is a signed distance function, so a function that gives you the distance to some surface, right? And a neural SDF is just an SDF that is being defined inside a little multi-layer perceptron like this. So you don't have an explicit surface like you would do if you had something like a mesh, right? This is a very explicit form of a surface. A neural SDF is going to be implicit because it's like the surface is being stored inside the weights of this little neural net right here. The neural SDF warps sampled points on camera rays from the warp state back to the static state. We optimize the backward warping and learn a forward warping as the inversion of the backward warping by employing a cycle loss. Okay, so the cycle loss is a reference to this. This is the cycle consistency loss on papers with code. So there's different versions of these, but like the basic idea of a cycle loss is that you have some mapping X to Y, and then you also have Y to X. So you basically have a way to go from one thing to the other thing, and then from that other thing back to the original thing, right? And these mappings should be reverses of each other, which means that what a cycle loss is really doing is it's basically saying, okay, if I take some X and I go and I feed it into this mapping, and then I feed it into the opposite or inverse mapping, I should get back the same thing, right? So this X and this X here should be the same. So it's a way of regularizing in a way, right? You're just pushing gradients, but you're pushing gradients in a way that's saying, okay, I'm learning this mapping, this warping, and I can also get the inverse of that warping. So if I warp and then inverse that warp, I should get the same thing back. And that's what this cycle loss is. So they're using this to make sure that this neural SDF is properly warping their Surfels. We initialize the MLP to obtain warping functions JTB by the MLP learned by the neural SDF part. So just like literally a throwaway sentence, but kind of a complicated setup, right? So they're using the MLP here that does the warping is actually initialized from the MLP here that is trained as a neural SDF. So multiple stages going on here, right? In your initialization stage, you're using this cycle loss where you're doing the forward warping and then you're doing the invert, and then you're basically saying, okay, well, if I forward and I invert, they should be the same thing. That's where that cycle loss goes in, and then I'm going to push gradients into this little multi-layer perceptron. Okay, now that I have this little multi-layer perceptron, I'm going to use it for this dynamic Gaussian splatting stage, or Gaussian Surfel stage, where I'm going to be doing the kind of more classic losses here, where I have the normal. I want the normal to be good, and I also want the final color of the thing to match the appearance of the generative video model. Fairly complicated little setup, but I don't know, part of the reason I read these papers is also just because it's like exercise. It's like an intellectual exercise to read these papers and try to understand them, right? If you can read this paper and understand it, and you do that consistently over the course of a year, by the end of the year, you're going to be much more comfortable with a lot of these ideas, or even new ideas, right? So like, I think this is how you learn, is like you approach something with which initially kind of looks difficult, and you're like, I don't know what the fuck this is. Like, there's 10 different steps here. Like, half of these steps I don't even understand. And then you learn it, and you're like, oh, you know what? Actually, this isn't that complicated. Like, sure, it's a lot of different moving pieces, but like, if I can understand each piece, now I have a better idea of this whole thing. And doing that over and over and over and over again, it's almost like the material doesn't matter. You're more learning the process of like understanding something makes you better at the process of understanding something new. So I don't know, part of this paper is just that, is that like, hey, even though it's kind of complicated, and even though it's really kind of just like a point on the current trajectory of technology that everyone's going to forget about, like soon enough we won't really need to know what dual quaternion blend skinning is. Like that's not necessarily something that you're going to be using all the time, but trying to understand dual quaternion blend skinning is like exercise for your brain, which you can then apply in a different place. Okay. Question from Ikel Fonxion. Which GPU do you personally use in your own projects? I have a 3090 and some 3070s and a 3060. I don't know. I don't really do like serious training though. I think if I wanted to do like serious training, I would probably use some kind of cloud GPU, A100s. Those are probably the standard. Maybe H100s if you're cool. You can get access to one of those. But I'm not doing a lot of serious training at home. What are they using here? Let's go into the implementation. So obviously this is a little MLP. It's going to have 8 layers. So this little MLP here has 3 layers. So imagine an 8-layer version of that. The dimension of the latent code embedding is 128. So this is the little extra information that you feed into your MLP. Where is it? Right here. This NERF style MLP, which outputs a 6-dimensional dual quaternion. It's conditioned on U, it's conditioned on T, and it's also conditioned on this learnable latent code. That learnable latent code is 128 dimensional. You have this hard-coded 25 bones, which I don't like that it's hard-coded, but you got to do what you got to do. They initialize the centers of the Gaussian surfels with the sampled surface points extracted from the neural SDF, right? The neural SDF is a implicit representation of a surface, and that SDF, or the sign distance function, is going to tell you how far away you are from a surface. So wherever that SDF says 0, that means that's going to be a surface. So you can basically just assume that's the surface and then just sample points along that surface, and that's where you're going to initialize your little surfels. Right? So you're going to be, the SDF is going to maybe give you some kind of smooth surface like this, right? You're going to evaluate it everywhere that it's 0. Then you're going to just initialize, sample along that surface, pick a bunch of surfels. They're not going to be all necessarily aligned, and then you're going to be using this multi-step optimization process, right, where the surfels and the little normal vectors of those, and then all of this together, it's all improving each other, right? Like all these losses, they're all kind of like, they're all pushing into the same Gaussian surfels. So over time, the Gaussian surfels get better and better and better. Training takes over 1 hour on an A800 GPU, which isn't too bad. No contribution, A+B paper. Yeah, it's definitely not like a super amazing paper, right? They're really just taking a bunch of different techniques, combining them all together, and then showing you that you can get some kind of cool results with that. But a lot of computer vision papers are like this, where it's just like, hey, here's like a multi-step optimization process with like 7 different losses and like 4 different regularization situations. And there you go. But my answer to that is that this is kind of what I was saying with the like, hey, part of this is just, you're just reading this to learn, right? It's like you're reading this just to like exercise your mind and like think about SO3 and think about rays and coordinate frames and rotations and normal vectors and warping. So I don't know, I'm just kind of reading this for entertainment purposes. Evaluation metrics are PSNR, SSIM, LPIPS. These are pretty standard. Pretty good. Obviously, you see here bold. So for all of these scenes, they have the highest score, but that's also because they're kind of comparing to things that they picked, right? So like they're not going to pick things that they compare unfavorably against, so they kind of pick some other things. Here you have deformable Gaussian splats, you have a NERF, so you at least have one NERF, you have one Gaussian splats, but maybe if they compared against a broader selection of things, they wouldn't have gotten the best score. Qualitatively, you get highly detailed textures, superior normal maps, and it enhances the robustness of our method against artifacts. I mean, these surfaces look clean. You know what I'm saying? Like, think about that. That surface is coming from an object inside a video, which is coming from a description that someone wrote. So this surface, which is quite clean, is literally just coming from some text that some random person wrote, right? I guess this is the prompt. I don't read Chinese, but maybe this is the prompt. So we're so close, guys. We're so close to this like metaverse, like simulation world where you can just literally talk a video game into existence, talk a 4-dimensional world into existence. These papers are getting closer and closer and closer every day. All right, ablations. The impact of the warp state normal regularization. When removing the regularization, there is a significant degradation in the structural integrity of the surface-aligned Gaussian surfels. Okay, so in these ablation studies, they remove different parts of it, right? this is a very complicated pipeline, so they're going to be like, okay, what happens if we get rid of this? If we get rid of this and we only push gradients from here, what happens? And the answer to that is if you remove that warp state normal regularization, you get significant degradation in the Gaussian surfels. If you remove the refinements, you lose the fine grained appearance detail and you get this kind of like texture flickering. So yeah, even though it's a complicated pipeline, if you remove any piece of this, it doesn't work as well. The only way to effectively remove pieces, quote unquote remove, is to increase the scale. And when you increase the scale, then a simpler approach will yield better results. If you keep the scale the same, you have to add more complexity in order to get good results. That's pretty much it. Let's look at the conclusion here. Vidu4D outperforms existing methods in both quantitative and qualitative evaluations, highlighting its superiority in generating realistic and immersive 4D content, reliance on video quality, scalability challenges, and computational difficulties in real-time applications. Okay. And that's pretty much it, guys. That's this paper. Brian, like always a great stream. Yeah, I appreciate it. Like I feel this week I was pretty busy, so like I didn't really, like some weeks I have enough time that I can like review a bunch of papers and I'll go through like, you know, multiple dozen papers and I'll like skim through them, look at the abstracts and then pick the best ones. But this week I didn't really have the time to do that. So I just kind of like very hastily just kind of picked 2 papers and I was like, fuck it. I picked the papers, I'm going to read them. And yeah, like halfway through this paper, I realized that like, hey, this paper isn't like amazing, but you know, sometimes you gotta eat your vegetables, right? It's like sometimes it's worth doing something even if it's not necessarily going to be life-changing because, you know, you're exercising a muscle, right? Like you're exercising your intellectual muscle here. All the different concepts in here require you to think about different things and then putting them all together. It's exercise, guys. That's what it is. But the results are pretty cool. Certainly gets me ideas of things to experiment with when I'm competent enough. Yeah. There's definitely something here, right? Like I feel like maybe it's famous last words, right? Because I remember when nerfs first came out, everyone was like, this is totally the fucking way to go. Nerfs are the way. And then Gaussian splats came out and we're like, all right, we're done playing with nerfs. Gaussian splats are the way to go. Obviously, Gaussian splats everything. And then Surfels came out and we're now like, oh, wait a second. Surfels are totally the way to go. Gaussian splats are trash, right? So how likely is it that we end up in another situation where something else comes out that works even better, right? Because when nerfs came out, people figured out a way to basically do this, right? 4-dimensional nerfs. Okay. Then Gaussian splats came out and people figured out a way to do 4-dimensional splats. And now Surfels came out and people are like, okay, here's a way to do 4-dimensional Surfels. So will there be a new type of 3D representation? And then will there be a new paper that shows you how to take that 3D representation and turn it into a 4D representation? Probably. Do I know what that's going to be? Not really. But does understanding nerfs and Gaussian splats help you understand Surfels? Yes. So does understanding Surfels mean that you're going to better understand whatever comes next? Yes. And that's really the whole point, right? Is that the point of learning nerfs and learning about 3DGS and learning about Surfels is so that you can better understand the next representation that's going to come out. Maybe just vibe with all these techniques. Yeah, that's all we're doing here. We're just vibing. We're just vibing with some warped state normal regularization. All right. Let me sip this water. Let me summarize this stream. All right, guys. Today we reviewed a nice little cozy computer vision paper. This stream was called Vidu4D. We reviewed this paper, Vidu4D, single-generated video to high-fidelity 4D reconstruction with dynamic Gaussian Surfels. This is a paper out of a couple different Chinese institutions here, including a startup that has the same exact logo as Meta. I don't know what's going on there. But what this paper is, it's kind of the first paper I've seen that takes the Gaussian Surfels, which are a successor to Gaussian splats. Although Gaussian Surfels have been around for a while, here's kind of an early 2000s paper that first introduces the idea of Surfels. Surfels are very similar to Gaussian splats, except they're two-dimensional, right? They're basically just this little coin. But because they're two-dimensional, they can align with the surface of an object, which means that you can use the normal direction of the surfel to improve the quality of the 3D representation. So you can see here, this is an example that I showed. This is a Gaussian splat. You see how kind of none of these are aligned with the surface. So they take Gaussian Surfels and they're like, hey, has anybody done four-dimensional Gaussian Surfels yet? And not that we know of. All right, let's fucking do it and let's publish that paper out. So they're going to do 4D Gaussian Surfels, but to make it extra interesting, rather than doing 4D Gaussian Surfels from real videos, they're going to be doing 4D Gaussian Surfels from generated videos. So the combination of those two things is why I read this, right? I read this paper because, okay, it's not just 4D Gaussian Surfels, but it's 4D Gaussian Surfels from generated videos. And that's the full pipeline, guys. Like, once you have 4D Gaussian Surfels from video generative models, that's text to 4D. Now we're talking text to 4D. Text to 4D is the basic building block of the metaverse, where you're sitting there with your headset and you're just speaking a world into existence, right? And it's a living world with objects that have explicit 3D surfaces that are moving around and doing things and interacting. This is the beginning of that. So the paper itself is a little bit complicated. There's a couple different pieces here. You have a multi-step pipeline. You have initialization stage. You have a DGS stage, the dynamic Gaussian Surfel stage. You have your standard kind of rendering kind of losses here, where you're just trying to make the surfels appear visually the same as the two-dimensional video. It's two-dimensional frames inside a three-dimensional video, but the third dimension there is time. But you're also doing this warp state normal regularization. So they do a lot. They create these bones. Bones are a term from the classic textured mesh world, where you define this armature composed of bones, which allows you to animate meshes. In order to do that, generally you have to define what are called, you have to solve this skinning problem. The skinning problem is figuring out which of the vertices are moving with which bones. And you can define that with skinning weights. Here you see the skinning weights for different parts of this 3D model. So you can see which bones affect which things. And there's a rich literature of different techniques that people have come up with to do this skinning in a way that results in visually correct things. Here you have dual quaternion skinning, which solves some of these what they call candy cane artifacts. Let's see if we can get that right here. Candy cane wrapper artifacts, which you'll see in like kind of old shitty video games. You'll see these appear. Dual quaternion skinning on bones, and the bones themselves are also learnable. So the bones are treated very similar to each of these little surfels, where they have some centers, some rotation matrix, some diagonal scaling matrix, and you're learning those, aka you're pushing gradients from these losses into those parameters. So over time, you're, rather than kind of these bones, which are hard code, like some human came in and physically placed these bones inside this object. In this case, what you're doing is you're learning the right bones. So your bones are moving over time. You're initializing to 25 bones, but then those bones themselves are kind of like moving and rotating over the course of this optimization process. Yeah, in terms of the actual neural nets being used here, everything is a little MLP. So they basically have this little tiny 8-layer MLP, very similar to a NERF, where you're taking your camera, two-dimensional camera frame, and then you're projecting a ray through every single pixel of that, and then taking that ray and seeing where it intersects your little Surfels, and then warping that specific little Surfel according to this little MLP here. You have some latent code there as well that's learnable so that you can warp in a more bone-specific way. So maybe one bone has a slightly different type of warping than a different bone, and so on. But yeah, that's pretty much it. Train this in 1 hour on an A800. The results are pretty cool, but they definitely are a little bit limited. So all of the examples that they give you are very object-centric. There's no background. It's a single object. So early days, but I can't wait to see what the next level version of this looks like. That's it, guys. Cozy, short little stream today. If you want another short little stream, join us tomorrow. We're going to be looking at, what's tomorrow? This one, Road Less Scheduled. So tomorrow we're going to go to the recent paper that came out. There was hype about this like months ago, it feels, but they finally released the paper. This is like a schedule-free optimizer. It's also going to be kind of intense and math-heavy, but if you're into this type of intellectual exercise, then you're welcome to join me. If not, have a great weekend. I appreciate you guys hanging out and watching. Thanks, Aries, something, Spirabel, Snooks, Brian, Chinese name, Ikilfonxion, SHC, 87GN, Show, Diga, Niraj, Oma, and Ed. Thanks, everybody. Have a great weekend, and see you guys possibly tomorrow.